Okay, I'm going to talk about r2frida, which is obviously a way to integrate r2 and Frida. How many people here doesn't know anything about Frida? Okay. Tried to squash the entire Frida in 2 slides. I don't know if it's enough, but well, Frida is an open source project created by Ole, which is there. Initially it was a one-man band, but then now there's a community which is growing. It's very nice. What it does is just to allow dynamic analysis of application by injecting a thread in an application, a running application, in user space, and then spawn a JavaScript engine from there. And there you have an agent, which is with which you can communicate back and forth with the application and run instrumentations on it. The target application may be also on a mobile device. This is the kind of things you can do. So from reading, writing process memory, or also to manipulate the metadata of the binary and access the exported functions or debug symbols, and you can interact with native functions both by calling them or maybe hooking them to be called when a function is called, and you can manipulate parameters at runtime or change the return value with the interceptor. Or also you can also access, if the Objective-C or Java runtime is present, you can access the list of all the classes and methods, and you can both implement classes or call methods or instance classes or interact with them runtime. There's another component of that is the Stalker, which instead of modify the code of the application in order to do some instrumentation, it hijacks the thread into a shadow copy of it, a modified copy with all the instrumentation. So you're able to do things like getting the list of all machine code instruction run and also manipulate them runtime. The idea is that Frida is a framework. You can build things on top of it. And for doing that, there are bindings in many languages, mostly C or Python or Swift too, maybe. Yeah. This is the breakdown of architectures and operating systems supported by Frida. Obviously, this can be grow. This is a growing list as soon as people add support for an architecture of interest, because it's the structure of Frida is that there's the lower level, which is machine dependent, and then going high to the levels, everything is portable. So from JavaScript, you can just hook the functions in the same way, depending from the operating system or architecture. Everything is abstracted. So for example, when you have your code instrument in Objective-C on Mac, probably it would work also the same also on iOS. Or okay, r2frida is implemented as an I/O plugin naturally, because since Frida provides read-write access to the process, you can just attach to a process and open its memory like a buffer in Radar, and so from there you can use the regular Radar commands, so you can go and analyze functions and disassembly stuff on the runtime application, the running application, but also provides this long list of commands, which we're going through these now, if you're ready, to provide also more features to R2, leveraging the Frida functionalities. So basically, all these features are aimed to do a debug of the application which is without a debugger, so it's scriptable and also more stealthy than the normal debugging. You can install it using r2pm or just clone it from Git. Okay. To start it up, you just have to use the Frida URL scheme, and there are two ways to run it. So you can attach to an existing process by specifying the name or the PID, or spawn a process by specifying the full path of the process with arguments too, if needed. And on the mobile device, you have to specify the package name. When you spawn a process with Frida, the process is suspended because it allows to instrument everything before the application even has the chance to run any code. So you can bypass also detection of injection or early things that are needed. But when you have to, when the instrumentation is done, you can just resume the process. The command to do that is dc. You see that there's a slash because at the beginning of all the commands, because these commands go through the r2frida plugin. So here I will go through every command. But to avoid you to fall asleep, I will make a quick demo now and show something live. So here I have a Twitter application running on my Mac. Can you read that or? Okay. I attach to it, and I mean, for example, I can here. These are the r2frida commands. So with backslash question mark, you get all the list, or mostly all the list. For example, here we have an objectives here on time, so we can, for example, list all classes. There are many, so because you have also all the system classes and everything. But for example, if I'm interested, for example, in only the app delegate, I can use the grep functionality of Radar and just see what's the name of the app delegate class. If I want to see their methods, it's like specifying also the class name to the IC command, and here the list of methods. For example, if we will go to the did finish launching method, we can just analyze it and go there. You can also emulate stuff. Can you read anything from that? Yeah. I can also do it like this. Still small or? Yeah. Okay. Okay. So, for example, here, can you read now? For example, here we are seeing method names because of emulations, but we can't see the function which is called. So, for example, we can, with the II command, I can import the imports from a module. For example, these are all libraries loaded with IL command. The first one is the application module. I can just import all the imports using this syntax. So now I can see that it's calling the message send method. So if I go down there, I can see, for example, that the shared Twitter method is called. So I want to see, for example, here we can see the method name, but we cannot know the class because Objective-C is resolving the method runtime. So one way to do that with Frida is just with the eval command, we can just run Frida JavaScript code inside this session. So for example, I can do API resolver, to which you can pass a query and resolve the method. For example, we don't know if it's static or not. We don't know the class name, but we know the name. And in this way, typo, obviously. Okay, we get that the class name for that method, and we can just use this information and explore more. These are the methods of the Twitter object, the Twitter class. For example, this is interesting. Sign in with username and password, for example. So you can just go there and so this is a way to explore the running application. Without knowing anything, you can just resolve things and import the symbols and make your way through reversing it. So this is really useful to analyze application. For example, here again, it's calling init with username and password. We can use again the same method we used before, the API resolver feature Frida, and get what's the class name, Twitter account. So it's init a Twitter account. What other initializers as this class? These. So for example, we can just what we can do is also tracing the calls to a function live. So I can place a trace point here. With the DTF command, I specify the function address. Sorry. And you can specify also the parameters, so they are printed. For example, here it's Objective-C, so the first one is the handle of the object. The second one is a C string with the method name, and then there are the parameters. So username and password, for example, we need. So we set that, and then we go to Twitter and just add an account, for example. And we see that the function is called and the parameters are printed here. For example, here is my password. As you see, this tracing is not blocking the radar session, but instead the output is just printed, but you can still run command. In this moment, this function is still traced, so if I call it again, it will print it again. If I'm not interested anymore, I can do just like this, and every trace is gone. So this is okay. I can do also another thing. For example, I can in the appDelegate class, I saw before there's in the initialization. It was calling something like switch to time with identifier. So now I want to call some Objective-C from here, and I want to do that. So let's see which class is this. Okay, tm team. Let's see what static methods it has. So for example, it has an interesting method which is switch to temp. I want to switch to the dark temp, for example. So since also it has a dark temp method, we can just try to do it with Frida and see what happens. So for example, we can do just eval. To access all the classes from Frida is like the object, and then you get the class name. And then I just call this method, which is a class method, so I don't need to allocate before. Okay. Oh, classes, yeah. Thanks. Okay, that's the one. If I call it like this, it will print only the handle, but actually there's an entire Objective-C object there, so I can just call stuff here. We have to call the switch to temp object with this parameter. Sorry. Okay. Some crazy mess happened, but it's because probably I had to call that method on the main thread, but it kindly worked, so. Okay. So I'll go on with the presentation now. And going through the commands. I'll go fast on the things we already seen. So, okay. Oh, nice. I didn't mention that. In order to get Radar to disassembly with the correct architecture, you have to tell him what's the right architecture and enginess. And the command to do that is this. This takes this information from Frida and make R2 execute the commands needed to initialize the configuration. So that's the first thing you have to do if you have to disassemble something. Probably this will change in future because it would be nice to do that automatically. So it's okay. This to list the libraries. Here the commands is not prefixed with anything, but to send the commands you have to prefix with the backslash or with the equal bang prefix. This is for the imports. You can list them or just get Radar commands and set flags for you. So you will have the Radar flags for each symbols. The same with the exports. And also you can find a single symbol on a library, for example, here with the open. The open symbol is exported by two libraries in probably different stuff, and you can list all the exported opens or just get the one you're interested in. The AC commands, we already saw that. The AP command is similar to IC, but for Objective-C protocols. You can resolve the reverse resolve symbol. For you can say, you can ask what symbol is defined as that address, but it works, but it's a bit slow because everything is indexed in the reverse in the reverse direction. So, oh yeah, you can search stuff in the memory of the process, and this is cool. I want to show you. For example, here I can search the memory of Twitter and, for example, find what Stefan Esser is saying now on my memory, and Samsung bug bounty product. Okay, it finds a bunch of them because they are the UI caches and the JSON objects and the HTTP requests, and so. But from there, it's nice. You can search things and see and search, for example, where these things are referenced. For example, by searching like this. Now I just use this command, the first one, but you can also search for a value with and it will account for the correct endianness. So you can search pointers where they are referenced and stuff. It's integrated with radar search, so you will get flags out of that. You can configure it with the normal evaluation configuration from radar, but also it has specific configurations. For example, you can restrict the search only to memory chunks with some permissions, or in the current the memory range containing the current offset, or filter by path if available. Now the debugging commands are the more juicy stuff here. Here all the debug commands start with the D to trying to be consistent with radar commands. You can just show the memory maps, and also to find the map which contains the current offset. You can change page permissions, or at least try to do it. You can hijack execution. There are mainly two ways to do that. One is to the DI command, which just replaces the return value of any function at address with the one you're specifying. Or you can just go and patch the code. The interesting thing here is that this flag makes it possible to patch code also on architecture which requires code signing, because it's using the Frida API, which dynamically pseudo-sign your patched code. You can allocate stuff on the heap that can be useful, for example, when you have to call some function from there and you need to pass a pointer to it for output parameters, or also for strings or stuff. The example here is that you can allocate a file name here, and you get the address of the allocation. All these allocations are kept alive, so you should deallocate that at some point if you wish with the DMA- command. Here it's like just allocating a string and 8 bytes. Then it writes some funny constant in the just allocated pointer, and you can see it with the radar commands that your data is there. You can also inspect the threads, the running threads. So you can get the PID, you can get the thread IDs, but you can also get the context of the threads, and, for example, see the registers values for every thread. And, for example, here it's just taking the stack pointer from the second thread and printing what's inside with radar. You can manipulate environment to both overwrite existing variables and also to define new ones. You can just load a library inside a running application. For example, here it's like inception, because we are injecting a radar core library in a running application and then calling commands inside that instance of radar, so and getting out the result from the memory. Yeah, this is how we call functions. So for example, you can pass both an address or a symbol name for a function. Here is calling the stat function, which takes two parameters. One is the file name, and the other one is a buffer, which will hold the result of the stat function. So we allocate them on the heap and then call the function, passing that pointers. At this point, we can just inspect the result using radar. So here I define a naive stat format and print it. With the dd command, you can manipulate file descriptors. This is cool to redirect output and input. For example, if you're debugging an application which takes the password and the standard input, you can do like that. You spawn it, so the process is suspended. During that time, you can just open the output file, or the standard input file, and then replace the file descriptor with your. So in this case, it's redirecting ls output to a file, but we can totally do the opposite and take the standard input from a file. Then you resume the process and everything is going piped. We already saw the DTF function to tracing the calls to functions, but we can also trace, instead of a function, just an address, which can also not be a function. It can be in the middle of a function, or can be in anywhere. In that case, it's as soon as the execution reaches that address, you will get the trace. By default, it will get the backtrace, but you can also specify if you want to print the content of some registers at that point. And all of this is non-blocking, like I showed before. If you want to block the execution at some point, we can use the breakpoints, which are not real breakpoints, but are Frida probes, which you place at some point, and when the code execution reaches that, it will wait. So this is non-blocking for radar session, but the thread of the application which reaches that breakpoint is blocked. So for example, here, this example is on ls. So if you run ls, we'll just call exit at the end. So I put a breakpoint on exit, and the process is not exiting until I do DC. This is useful when you want to do some analysis before for example, the program is exiting, but you can place breakpoints anywhere. Okay, this is a new feature which we added recently. It traces stuff using the Stalker, which again is a way to hijack the thread to a modified copy of the code. So in this way, we can, for example, you want to know what gets executed when a function is run. So you can say DTSF that function, and you will get the entire disassembly of all the code that is run from the beginning to the end of the function, but also the functions called by the functions and so on. So it may be huge, but it may be useful in some cases. I want to show that in Linux this time. Maybe it's a bit small. Okay. The perfect use case for this is the white box qualification from the riskier challenges, because it's a highly obfuscated binary, and if you, like me, you don't know anything about cryptography and white box in particular, it's useful to understand what's going on. Here, the binary is taking the password from the first parameter, so I use r2frida to spawn it. The process is suspended at this point, so, but as soon as I resume it, it will exit because everything is really fast. So I just put a breakpoint and exit here. Then I want to stalk the main function, but I don't know the address. In this case, it's easy because the binary is not dynamically relocated at every execution. So, for example, we can just do this and get the address of main. We should configure it a bit because we want to restrict the amount of code as much as possible. So, for example, we stalk only the code coming from the app and not from external libraries or any other module. And we want the, instead of compile, okay, this is something I have to say. Stalker event chooses the type of event you want to stalk. For example, if you choose call, you will get only calls. The same for ret. Exec instead will notify you for every single machine code instruction executed, which may be overwhelming when there are many codes, very much code running. Instead, the block event happens every time a basic block is executed. Also, if it's executed more than one time, so you will get the real order of execution of every basic block. Instead, the compile one is emitted only when the basic block is executed the first time. We want block here. So DTS F for function. The address is the main here. Oh shit. Damn Ubuntu. Okay. This in this moment the process is suspended, but when I will issue this command, it will be resumed automatically. And after some point, yeah, we will get a shitload of code, but this is good because, for example, I do that again now more fastly. If you redirect that, for example, to an editor, you can, after some seconds, yeah. For example, here in the zoom out view here, you will see the trace of the execution from really above, but it's enough to understand the patterns. For example, here is loading very much stuff from memory, is writing stuff, and then at some point some repeating actions, and then these long blocks. Long block, there are like a pattern of long blocks, and then after 4 long blocks there is a small one. So and if you go down, this stuff repeats 10 times. So this is a huge indicator of what kind of crypto algorithm is here. But yeah, I will not go on that. The other thing you can do is instead of just dumping all the assembly, you can put that information in the existing trace in the trace SDB of Radar, and then get the results with the DT commands. So you can try it. In this way, it will generate the radar commands, and with the dot at the beginning, we're executing that commands, and the result of that is that we are taking that into the trace SDB. After a few seconds. The advantage of that is that at the end of this process, I will get, for example, statistics on how many times that address has been executed for free. And this is better than going in Sublime Text and see the repeating patterns. For example, with the DT command, you will get for every address the times it gets executed. For example, here they are repeating 16 times or 36 times. And then you can also DTD and just disassemble everything that has run on the last session. So this is really useful to understand what's going on when you have obfuscated code and you don't know how to reverse it by hand in reasonable time. Okay. Yeah. 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 Yeah, because in the first run, that code, that disassembly is generated from Frida, so from inside the process, we using a capstone instance injected by Frida inside the process. Instead, in the second example, the disassembly is done by Radar. So what we do in Frida in that case is just collect the addresses of all the basic blocks executed, and then elaborate that in Radar later.
Like when you, I'm sorry. So let me repeat. I'm curious if the values we are getting in this disassembly, what you are showing now on the screen, if those values are the runtime values. So
no, the values are not the runtime values in this case, because we are just disassembly at that address, but in a different time. So
yes.
Yeah.
Yes, this is my problem. So is it possible to do it runtime? Do you see a way to do it?
Is it possible? Yeah, there are ways to do that. They're not yet implemented, but yes, I think it's possible. Both by improving the first disassembly you saw,
yes.
or both trying to store also the state of the registers for every instruction executed, but that may be very much data to store.
Yeah, so I think the first version has to be more.
Yeah, another kind of thing that we can do is just synchronously do that. So, for example,
yeah.
Every time an event is emitted from Frida, just block there and analyze that the values, and then let the execution proceed. So that's another option.
Thank you.
Okay, we already saw that. already saw that. So now a brief introduction of to extend r2frida beyond what is currently doing. For example, we already saw which if something is missing on the, you need some Frida command which is not in r2frida, you can just eval and execute it. It also supports the script style scripting using Mjolnir, which is a library which basically it's a compatibility layer between the script syntax and Frida, translating that to JavaScript. And but you have to compile. It's not enabled by default. I think you have to compile the plugin with the proper flag. It's described in the makefile. You can also run JavaScript scripts you already have. For example, if you have scripts used to run in Frida normally, you can just load it from here with the dot command. If you need some more full-featured stuff, you can just write your plugins here. So plugins are regular JavaScript files that register themselves with using this global object. So they just register themselves with a name, and at this point they are called back as soon as the user types a command, and the plugin can choose to implement that command. For example, here it's the resolver we used using eval in the previous example. Here it's turned into a plugin, so I can show that. I can just load the plugin, which is in this directory, so it's just dot and the path to the plugin. At this point, I have the resolve command, which will take a query in the resolver syntax. So, like, we can do like that and have a nice output of the resolver. Yeah, the idea is that you can do your stuff on top of that and share it with everyone, or just decide to keep it private. And the other way is to extend r2frida going to the repository and and contributing, because it's pretty simple actually. It's just a C file for the IO plugin and a JavaScript file for the agent. For me, it's over. So if you have questions. Thanks.